Every time you flip a switch, you're asking the universe a favor. Hey, could you move a few billion electrons over here? And somehow, it just happens. We plug in, charge up, and never really wonder what's behind that glow. But the truth is, behind every outlet is one of humanity's largest and most fragile inventions. It's called the grid, a machine that spans the continent, reacts in milliseconds, and somehow keeps the lights on almost all the time. So how does something so huge, so powerful, and so invisible actually work? And why can a single mistake send millions into darkness? The grid is basically an enormous game of connect the dots. At one end are the power plants: coal, gas, nuclear, hydro, wind, solar, each turning energy into electricity by spinning a turbine or using sunlight to excite electrons. These are the grid's generators, the muscle that gets everything moving. From there, electricity leaves the plant through step-up transformers, which boost the voltage to hundreds of thousands of volts so it can travel long distances efficiently. High voltage means less energy lost as heat, like turning up the pressure in a water pipe so the flow can reach even further. Those giant metal towers carrying cables across fields and highways? Those are the transmission lines. They're the interstate of the grid, moving power between cities and states. Eventually, the energy arrives at a substation, where another transformer steps the voltage back down for local use. From here, it splits into smaller distribution lines, the wooden pole wires you see along roads and alleys. Near the end of those lines sits a gray, can-shaped device on a pole or a green box on the ground. That's a distribution transformer. It's the last voltage drop, turning thousands of volts into the 120 or 240 volts that your home appliances can use safely. From that transformer, short service lines run to your house, into a meter box that measures your usage, through your breaker panel, and finally into the outlets and light switches you use every day. So when you flip a switch, you're completing a journey that started miles away, from generator to transmission tower to substation to transformer to your wall. But here's something wild. There's almost no storage anywhere in this system. Electricity isn't like water in a tank. You can't fill it up for later. Every watt you use has to be produced the instant you use it. That means when you turn on a light, a generator somewhere has to instantly spin just a little faster. And when you turn it off, it slows back down. All day, every day, that balance rises and falls like the world's biggest metronome. Here's another twist. The electrons in the wire by your house aren't racing hundreds of miles from that power plant. They're mostly just wiggling in place. The energy moves through them like a ripple moving through a crowd at a stadium. That back and forth motion, not the electrons themselves traveling far, is what powers your life. So what happens to power that isn't used? Well, it doesn't just pile up. Excess energy turns into heat or is automatically rejected by the system. Operators constantly throttle generation like easing off a gas pedal to keep output perfectly matched to demand. A few facilities can store power, like pumped hydro plants, which use extra energy to pump water uphill, then release it later to make electricity again. But storage still makes up less than 1% of America's total capacity. So the grid? It's a real-time balancing act that never, ever stops. To keep everything synchronized, the US grid hums at a rhythm of 60 hertz. That's the electrical heartbeat of North America. But what does that actually mean? It means the electric current in your wall outlet isn't a one-way flow. It's alternating current, AC. Invisible waves of energy moving back and forth through copper wires 60 times a second. If you've ever seen a guitar string vibrating, that's frequency. Back and forth motion creating a steady tone. The grid works the same way, except instead of sound, that vibration carries power. When everything is working, that rhythm stays almost perfectly steady, 60 hertz on the dot. If demand suddenly jumps, say everyone turns on their air conditioner at once, generators feel the extra drag. They slow down just a little and the frequency dips below 60. If that dip gets too deep, protective systems start disconnecting equipment to keep it from burning out. That's what a rolling blackout actually is. the grid taking pieces of itself offline before they break. The opposite can happen too. If there's more supply than demand, generators spin faster, frequency rises, and power lines can overheat. In both cases, the rhythm slips and the entire system wobbles. Keeping that balance is the grid operator's full-time job. They watch frequency like a doctor monitoring a patient's pulse. Tiny fluctuations, 1/100th of a hertz here or there, tell them when to fire up backup turbines or to dial others down. It's a constant push and pull between generation and consumption. So when we say the grid runs at 60 hertz, we're really saying that every power plant, every transformer, and every light bulb in your house is dancing to the same beat. And even if just a few dancers fall out of step, the whole performance can crash. If you like finding out how the ordinary world secretly works, hit subscribe. It keeps our signal balanced. Here in the United States, there isn't one big grid. There are three: the Eastern Interconnection, the Western Interconnection, and Texas, which mostly does its own thing. Each grid is a dense web of power lines, substations, and control stations run by hundreds of different entities. There's no single master switch or central brain, just a loose federation of utilities trying to stay in sync. That design made sense when the grid was built. Most of it dates back to the mid-1900s, when power mostly flowed one way, from huge plants out to homes and factories. Back then, nobody imagined solar panels feeding power back into the system or millions of electric cars charging at night. Today, that one-way architecture is being asked to do two-way traffic, and it is a strain. And there's something else most people never learn. High voltage isn't dangerous because it's powerful, it's efficient. The higher the voltage, the less energy is lost as heat while traveling long distances. That's why those tall metal towers hum. They're carrying power at hundreds of thousands of volts so it can move hundreds of miles with minimal loss. And yes, those birds sitting on the wires are perfectly fine. They're touching just one wire, so the electricity has no reason to pass through them. Why that works and what happens when they don't, that's a different video. Old equipment wasn't built for that kind of constant variability. Transformers can't easily handle the rapid up and downs of renewable power. High voltage lines already run near capacity, leaving little room for surges or reroutes. And even when new lines are approved, they take years, sometimes a decade to build, crossing multiple states and countless regulatory hurdles. The result? A national grid built in the 1900s, now being asked to power the 2000s. When people say the grid went down, it's not a giant switch flipping off. It's a chain reaction. A tree branch hits a line, causing a short circuit. That line trips a protective breaker and dumps its load onto neighboring lines. Those suddenly carry more power than they're rated for, heat up, and they trip too. Each failure adds stress to the next until the system collapses under its own protection protocols. And when your house loses power but your neighbor's doesn't, that's because the grid is split into thousands of circuits and feeders. Each one feeds a different cluster of homes, like twigs on a tree. If your twig breaks, protective devices called breakers or reclosers isolate just that branch, keeping the rest alive. Once that happens, line workers, or linemen, become the detectives of the grid. From control centers, crews can see which circuits are dead, but not always why. They drive or fly line routes, scanning for downed trees, damaged insulators, or broken connectors. Sometimes they use infrared cameras to spot hotspots that signal faults. When they find the problem, they physically repair it, splicing in new wire, replacing blown fuses, or swapping out an entire transformer. Each repair has to be tested and re-energized carefully so the surge doesn't trip something else downstream. It's dangerous, methodical work, often done at night or in storms, just to bring a few neighborhoods back online. But sometimes, the problem is much bigger than a broken twig. Take the Texas freeze of 2021. A brutal winter storm swept across the state, freezing natural gas pipelines, icing over wind turbines, and shutting down power plants that weren't built for sub-freezing temperatures. As generation failed, the frequency of the Texas grid, which normally hums steadily at 60 Hz, started to fall. If it had dropped much lower, the imbalance could have set off cascading collapse. Generators would have automatically disconnected to protect themselves, which would have caused more plants to overload and trip offline. Within minutes, nearly the entire state could have gone dark at once. And here's the scary part. If that full collapse had happened, Restarting the grid might have taken weeks or even months. You can't just reboot an entire state's worth of power plants at once. Most generators need electricity from the grid itself to restart, a process called a black start. Without some plants still running, there'd be no way to provide that jumpstart. So operators made a painful choice: rolling blackouts. They deliberately cut power to entire sections of the grid, rotating the outages to reduce total demand and keep the remaining system stable. By taking smaller areas offline, they gave the rest of the grid breathing room to recover its balance. It wasn't about punishing customers, it was about saving the infrastructure from burning itself out. Still, the results were devastating. Millions lost power and heat for days. Pipes burst, grocery stores emptied, and whole cities ground to a halt. It was a chilling reminder that the systems keeping us warm can freeze too. Over the next several days, utility crews thawed frozen equipment and gradually brought generation back online, one plant, one region at a time. Each new source had to be synchronized to that same 60 Hz rhythm before reconnecting. Piece by piece, the grid came back to life. That freeze exposed exactly how close we can come to a complete collapse, and how the very systems designed to save the grid can still leave millions in the dark. So why aren't we upgrading faster? Well, money for starters. Experts estimate modernizing America's grid could cost trillions. Utilities want to recover that through higher rates. Regulators and taxpayers push back. Meanwhile, most utilities earn profits from building new infrastructure, not maintaining old, so there's little incentive to fix what already exists. And then there's bureaucracy. Every new transmission project crosses jurisdictions, property lines, and courtrooms. A single high voltage line may need approvals from a dozen agencies before a single shovel hits the dirt. Technology adds another layer. There's no universal smart grid standard. Some regions run advanced digital systems. Others rely on analog relays older than your grandparents. It's like trying to upgrade half the internet while the other half still uses dial-up. And what's a smart grid anyway? It's basically an electricity network with sensors, automation, and data, a grid that can spot a problem and reroute power in seconds, kind of like GPS traffic rerouting around an accident. What about microgrids? Well, those are smaller, self-contained networks, neighborhoods or campuses that can disconnect from the main grid and run on their own using solar panels, batteries, or generators. When disaster strikes, they can keep the lights on locally even if the wider grid goes dark. And that's where the debate lies. Do we double down on massive, centralized systems powered by big plants, or build thousands of smaller, smarter networks that can think for themselves? Both paths have pros and cons, but there's one thing that's certain. As we plug in more cars, solar panels, and devices, the grid must become smarter, faster, and more flexible. Because the world it was built for, one of steady demand and predictable generation, that doesn't exist anymore. So the next time you flip a switch, remember what just happened. Somewhere, turbines spun, electrons raced, and a continent-sized machine adjusted itself in perfect sync. Also, your kitchen could be a little brighter. It's one of humanity's greatest achievements, and one of its most fragile. Thanks for watching. If you enjoyed this stroll through history, give us a like and subscribe for more curiosity-driven videos every other week.